Hello, this is Mr. Keaton here to talk to you about video 8.4a and mathematical induction. Mathematical induction is a way of proving things using patterns. So this by the way, I'm doing this on my tablet, and it's kind of awkward to write on. My sound is not working on my Promethean board, so I'll do my best here. So state the principle of mathematical induction. Let P of n be a statement involving the positive integers n. So if P of 1 is true, so you establish that the first one is true, then if you can find, and then anytime P of k is true, that is some random one, and the random one after it, P of k plus 1, so that might be the fifth term, and then the sixth term. If you can establish that the fifth and sixth and seventh seem to work, then you can probably say that P of n works all the time. And that's the concept of mathematical induction. You look for a pattern. If it seems to be working multiple times, and you can say P of k works, P of k plus 1 works, then P of n should work also. So in this problem, it says use mathematical to prove the following, that S of n equals 1 plus 2 plus 3 plus 4 all the way up to n equals this. And so we're going to do that by saying n equals to k and n equals to k plus 1, and then we're going to see if we can solve for S of n. So we're going to do this by saying let's let n equal k, and if that's the case, we'll stick k up in here, and that's going to be 1 plus 2 plus 3 plus 4 all the way up to k. And we know the sum of a arithmetic sequence is equal to the number of terms, n times n plus 1 over 2. So we get this formula, k is equal to k plus 1 over 2. And we have this formula already. So is it true, though, is the question. That's the sum of an arithmetic sequence. So we can say S of k plus 1 must be equal to 1 plus 2 plus 3 plus 4 and dot all the way up to k plus k plus 1, which is the next term. We had k plus 1 here, right? So there's k, that's all plus k plus 1. And we know that S of k plus 1 is that thing above. And this first clump is the same as this up here, isn't it? So we know that k times k plus 1 all divided by 2 is the first chunk, and then we have plus k plus 1. So that must be equal to S of k plus 1. So let's see if we can simplify that. Wow, we have a common factor of k plus 1. I'm going to factor that out. K plus 1. Both terms have that. And we're left with k over 2 plus 1 of the k plus 1s. So I factor, let's see if I can highlight that and make that clear. We factored out a k plus 1, which is right there. And we're left with k over 2 plus 1. So now we're going to try and simplify that a little farther. And to simplify that, let's see if we can find a common denominator and combine these. So that gives me k over 2 plus common denominator of 2, so 2 over 2 times k plus 1. And now on that right there, I can go ahead and factor out a 1/2, can't I? So now I have k plus 1, I don't like this head, times 1/2 times k plus 2. And that k plus 2 I can write as k plus 1 plus 1. That's the same as k plus, and all times k plus 1 times 1/2. And this, S of k plus 1, therefore, is equal to k plus 1 times k plus 1 plus 1 all divided by 2, which looks remarkably similar to this, except instead of k, we have k plus 1. So we've just proven that s of k plus 1 is equal to this up here, and we can use that formula over and over and over. And therefore, the formula is valid for all positive integers n because it fits into the same form. We just add 1 instead of n and n plus 1, we're going to get n plus 1 and n plus 1 plus 1. So by mathematical induction, we've proven that this formula works because it works for k and it works for k plus 1. Let's go ahead and try that same process for this problem here. It says use mathematical induction to prove the problem following formula. So we've got 1 cubed is equal to 1 squared plus 1 squared. 1 squared is 1, 1 plus 1 squared gives me 2 squared, which is 4. 4 divided by 4 is, so I get 4 divided by 4, which is 1. So 1 cubed does indeed equal this. So what we're going to do is we're going to go ahead and substitute n equal to k, and then test it for n equal to k plus 1 and see if it also applies. So s of k is going to equal to 1 cubed plus 2 cubed plus 3 cubed all the way to n cubed, which is going to be equal to n squared, n plus 1 squared all over 4. Now, in this case, we should have actually used k here. K squared times k plus 1 squared all over 4. So, if we can show this works for k plus 1 also, and it simplifies down to the same form, then we can conclude that this is the correct formula and it works all the time. So here we go. K plus 1 is going to give us 1 cubed again plus 2 cubed plus 3 cubed all the way up to k cubed plus k plus 1 cubed. Well, I'm good with that. So let's see where that takes us. So we know that the first chunk here, not including the last term, is equal to k squared times k plus 1 squared all divided by 4. We have that from the line above, plus we have k cubed. So the question is, how can we combine those? So we can say, made a little bit of mistake here. Got distracted by a student. This should have been k plus 1 cubed, which is this last term right here. So that needs to be brought over. And now we'll just continue with that. So out of that, I'm going to go ahead and factor. We have a common factor of k plus 1 squared. So I'm taking that out of these two terms, there and there, leaving me with k squared over 4 plus a k plus 1. And once again, I'd kind of like to combine these two, so I need a common denominator. So I'm going to multiply this one on the right here by 4 over 4, and this one by k plus 1 over k plus 1. And now when I take this down, I have another k plus 1, right? I can factor out, which gives me k plus 1 Another k plus 1 in the numerator that I can take out gives me k plus 1 cubed times oh, I got an error there. I got to back up a step. Let's see. Let's take that back. I didn't need to multiply top and bottom by k plus 1, did I? All I needed was that 4. So I'm going to erase this. We did not need that. This is k squared all over 4. And here I needed my common denominator of 4, top and bottom. So all I can really factor out is a 1/4, huh? So now I have k plus 1 squared, and I can take a 1/4 out. And I'm left inside here with k squared plus 4 times k plus 1. And let's go ahead and distribute that. It gives me k squared plus 4k plus 4 all times 1/4 k plus 1 squared. And if we slide this down a little bit, this right side here is going to factor to k plus 2 times k plus 2. Then we have our k plus 2, k plus 1 squared. And k plus 2 times k plus 2 could be written as k plus 1 plus 1 times k plus 1 plus 1. Which means we've got this 1/4 here, and k plus 1 squared gives us k plus 1 squared times k plus 1 plus 1 squared, all divided by 4, which is exactly what we wanted. So we did it. We proved it by mathematical induction that it works for k and it works for k plus 1, thus the formula works for them all. Tell me your favorite flower for question number 1. Have a nice evening.